Hello everyone, welcome back to our lesson on trigonometry. In this video, I'll be explaining the second part of trigonometry, which are titled Trigonometry II. If you are yet to watch the first part, I'll encourage you to do so before you watch this part. And in this video, our concern shall be on Pythagoras Theorem. The objectives of the lesson are given as follows. At the end of this lesson, you should be able to apply the trigonometrical ratios, that is tangent, sine, and cosine, to solve right-angled triangles. You should be able to combine trigonometrical ratios with Pythagoras Theorem to solve right-angled triangles. And finally, you should be able to derive the trigonometrical ratios of some special angles, that is 45 degrees, 60 degrees, and 30 degrees. And you should be able to use them to solve related problems. In this particular video, we are concerned about objectives 2 and 3, because we've discussed intensively objective 1 in the previous video. Again, try and see the video before you continue with this one. And here are the terminologies which we've already described in the previous video, and also symbols that we shall be looking at throughout this lesson. We've been discussed in the previous video also. And here is my focus in this video, Pythagoras Theorem. Before stating the theorem, I would like to show you some demonstration before I state the theorem. Let me take you to another application. All right. So here we are. I believe you all know a right-angled triangle. I want to demonstrate the Pythagoras theorem for you before giving you the statement. Now first, let me draw a right-angled triangle of a right-angled triangle ABC, where the right angle is at vertex A. The hypotenuse side BC is length 5 centimeters, while the other two sides BA or AB is 4 centimeters and AC 3 centimeters. Now imagine that we draw a square by the side AC, just like this. The square is of length 3 by 3. Length 3 by 3. Why? Because the length of the side AC is 3 centimeters. Now let's add some vertical lines and horizontal lines. So there are 2 vertical lines and 2 horizontal lines forming squares of 1 unit, or a unit squared unit, 1 centimeter squared unit, or 1 centimeter squared. So here is a square of 1 centimeter, square of 1 centimeter each. There is a length, so the area is 1 centimeter squared, another area of 1 centimeter squared. All right, to get the total area of this square, what do? We add up. We count all the squares. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. You observe that there are 9 squares all in this single 3 by 3 square. Right? So how do you get 9 in that case? You can look at it from this perspective, or that when you square 3, that will give 9. Okay. Next, let's add another square of length 4 by 4 alongside AB. All right. So we introduce vertical lines, 3 vertical lines, and 3 horizontal lines, and that will produce 16 squares. Let's count 16 squares of area 1 centimeter squared. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so, and that is just looking at it as in squared 4, you get 16 squared. Okay, now let's do the same thing to the length of the triangle BC, which is 5 centimeters squared. Add a 5 by 5 centimeters squared, 5 by 5 centimeters squared. Then I introduce the vertical lines and horizontal lines. Now, vertical and horizontal lines intersect to form 25 squares. Let's of unit 1 centimeter square. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So you see, that gives what? 25 squared. That's 5 squared equals 25. Now, if you take very close notes or very close observation on what you have on the screen, you will observe that when you add 16 plus 9, that will be equal to 25. All right? So you see, 3 squared, which is equal to 9, and 4 squared is equal to 16. 16 plus 5 is 25. So what can you now say about this activity or this demonstration? Whenever you have any right-angled triangle, what you've done here is true for all right-angled triangles. When you square, you just like to see in square to the hypotenuse side, which is the longest side of right-angled triangle. The square is equal to the sum of the squares of other two sides. All right, so this is what gave birth to the Pythagoras Theorem. That gave birth to the Pythagoras Theorem. All right, so let's continue now. And see, when you bring in the Pythagoras Theorem to this diagram you have over here, with the label, the side labeled A, B, C. In the diagram, you have A squared is equal to B squared plus C squared. According to the Pythagoras theorem, it states that in any right angle triangle, the square of the hypotenuse side is equal to the sum of the squares of other two sides, just like you've seen in the previous, in just my last demonstration. Okay. So, from the geometrical point of view, Pythagoras theorem gives the relationship between areas of squares and sides of a right-angled triangle. But from an algebraic point of view, the formula A squared equals B squared plus C squared can be used to solve right-angled triangles. So that is this is what this equation is, an equation we find handy throughout this lesson, and it is derived from the Pythagoras theorem. Try as much as possible not to forget this. Let's look at example 6. We've done 5 examples in the previous video, so the continuation, like I said earlier. Example 6. The sides of the rhombus are 17 centimeters long. If one diagonal is 30 centimeters long, what is the length of the other diagonal? So here is a wild question. And also example 7 says a chord 6.6 centimeters long is 5.6 centimeters from the center of a circle. A. Calculate the radius of the circle. B. Hence, calculate the length of a chord, which is 6.3 centimeters from the center of the circle. Okay, let's see the solutions to those examples 6 and 7. So here is the solution to example 6 at the left side of my screen. And I gave a quick sketch, a rough sketch of the rhombus. It's of length 17 centimeters all through, and one of the diagonal is 30 centimeters. Now recall that we are taught in geometry, while we're discussing geometry, we looked at some properties of a rhombus, and one of the properties of a rhombus that will come find handy in solving this problem is that property that states that the diagonals of the rhombus bisect each other at 90 degrees. When we say it bisects each other, it means it divides each other by equal half. Okay, this diagonal divides this into 2 equal parts, while the shorter one divides this one also into 2 equal parts. And they form 90 degrees. They meet at 90, they intersect at 90 degrees. Therefore, from that property, we can actually extract one of the right angle triangles from the rhombus. If you look at it properly, you'll discover that there are 4 right angle triangles equal, not just 4, but 4 equal right angle triangles, or congruent right angle triangles. So if one of them is extracted to the right. So, and from the right angle triangle, you can see the hypotenuse side is 17 centimeters, the other side is 15 centimeters, while the unknown, which is half of the shorter diagonal or half of the other diagonal we're supposed to calculate, are labeled as x. Now, applying Pythagoras Theorem, we have the hypotenuse side 17 squared is equal to the sum of the other 2 sides, x squared plus 15 squared. Collecting like terms, you have x squared equals 17 squared minus 15 squared. X squared is equal to 289 minus 225. That is x squared equals 64. Therefore, x is equal to the square root of 64, which is equal to 8 centimeters. That is the half part of the unknown length of diagonal is 8 centimeters. Since this other diagonal divides it into 2 equal parts, meaning to get the length of the other diagonal, the full diagonal, you multiply 8 by 2, or we add 8 by 8, 8 to 8, so that is 16 centimeters. I hope this explanation was clear enough. All right, so I want you to look at it, watch it again and again until you understand it clearly or better. Example 7. A chord 6.6 centimeters long is 5.6 centimeters from the center of the circle. Calculate the radius of the circle and hence calculate the length of the chord, which is 6.3 centimeters from the center of the circle. So here is a circle and this is the chord. The chord is 6.6 centimeters in length, while the distance of the chord from the center of the circle is 5.6 centimeters. The distance from the center to the chord which meets at the circumference of the circle is known as the radius of the circle, r. So when you extract the right angle triangle formed in the circle, it forms that shape. It forms this right angle triangle by the side of the circle. All right. Now, okay, I don't want to say recall, But let me just state it that there's a theorem in circle geometry. I know you don't know of that. Uh, I'm applying the theorem here. The theorem states that any straight line that is drawn from the center of the circle to a chord in the circle is a perpendicular bisector of the chord. Now, the distance from the center of the circle to the chord is that straight line. Now, it's going to bisect this chord into two equal halves, and it forms right angles with the chord. That is why you see me write 3.3 here, because this line has divided the chord into two equal parts, and it's forming right angles. So that is the reason why I'm sure that this triangle is a right angle triangle, and the length from the center of the chord to the circumference, or TS, the circumference is 3.3. And with that, you can also apply Pythagoras theorem to solve for the radius of the circle. That is r squared equals 5.6 squared plus 3.3 squared. 5.6 squared is equal to 31.36 plus 10.89, which is 3.3 squared. Now, r squared is equal to 42.25, the sum of these two. Therefore, r is equal to the square root of 42.25, which is equal to 6.5 centimeters. So as the radius of the circle is 6.5 centimeters. Now, next second part, it says calculate the length, okay, of the chord, which is 6.3 centimeters away. So we in this case, we want to calculate, we want to solve for the length of the chord. All right. The length of the chord is unknown, but we solve for the radius. So the length of the chord, let's say, let this L represent half of the length of the chord. So which is just, if I substitute this 3.3 for L, in case this is unknown, and this one becomes 6.3. That is L squared equals 6.5, which is the length of the radius of the circle, which is also solved for here, minus 6.3 squared. That is the distance from the center of the circle to the chord. So don't forget, I said again, the L here represents half of the length of the chord, and that will form the other side of the right angle triangle. The L squared equals 42.25 minus 39.69. L squared equals 2.57, 2.56 rather. Then the square root of L equals the square root of 2.56, which is 1.6 centimeters. Hence, the length of the chord, which is 6.3 centimeters from the center of the circle, is 3.2 centimeters. When you multiply 1.6 centimeters by 2, you get 3.6 centimeters. All right, so I believe and I hope that my explanations were clear enough. Those explanations are clear enough. All right, let's look at the next thing. So here I have some exercises for you to attend, and you're encouraged or advised to make a sketch of the given information when necessary. The sketch of the information will help you solve the problem very easily. So I'm going to create a post where you submit these solutions to these exercises. I expect you to do so before the end of the class. Next, this is the next theorem. We have theorem 9. And the theorem statement goes thus: in a right angle triangle, the square on the hypotenuse is equal to the sum of the squares on the other two sides. That is the statement of Pythagoras theorem. And this theorem we shall not prove. There is not going to be a proof of this theorem in this video or in the next video. If you're interested in knowing the proof to the theorem, I would advise you to consult our reference text, which is New General Mathematics for SS1. Let's look at our example 8. But okay, I want to go back to theorem 9. Please, like I've said earlier, the proof of this theorem is not going to be done in this video, neither is it going to be done in the next video. I'm not interested in the proof, but at least you should know the statement of the theorem. Whenever you're asked to state Pythagoras theorem, you should be able to state it clearly and correctly. So I'll encourage you to all memorize the theorem, at least for now. And later I believe you understand it when you see the proof. So let's now go to example 8. AB line segment AB and AC are the equal sides of an isosceles triangle ABC, and AD is an altitude. Prove that length AB squared plus AC squared is equal to 2AD squared plus half BC squared. Alright, this is a nice and a lovely question, and let me show you the solution to that question. Very lovely one. So here is the solution. First, I made a sketch of the question, the information given. So here is the isosceles triangle ABC, and we're told that D is the point on BC that's the altitude intersect with, or the line where the altitude meets at, the point where the altitude meets at BC. So A is the altitude. Now, if you look at the triangle carefully, it said in triangle ABD, this right angle triangle over here, length AB squared is equal to AD squared plus BD squared. That is my claim. And if you agree with my claim, I believe you should know the reason. I don't want to guess the reason. Okay, very good. The reason is because according to Pythagoras Theorem, the square of the hypotenuse side is equal to the sum of the squares of other two sides. It's just the application of Pythagoras Theorem. I labeled that as equation 1. Also, in triangle ABC, AC squared, which is the hypotenuse, is equal to AD squared plus BC squared. Or also the application of Pythagoras Theorem. Now in triangle ABC, the bigger triangle, the biggest triangle in the figure, BC is equal to BD plus BC. Of course, the altitude of the triangle will bisect line BC, and will be the perpendicular bisector of line BC. But BD is equal to BC, of course, they are equal in length. Therefore, length BC is equal to BD plus BD. Since BC is equal to BD, I have substituted BC for BD. So hence, length BC is equal to 2BD, which implies that BD is equal to 1 over 2 BC. And I labeled that as equation 3. Don't forget what we are asked to prove. I want to prove that AB squared plus AC squared equals 2AD squared plus half BC squared. Now, if you look at equations 1, 2, and 3, you would agree with me that we are approaching the solution. So, next step is to add equations 1 and 2. That is, I'm adding the left-hand side together and adding the right-hand side together. So what do I have at the left-hand side of equation 1? AB squared. Here. And the term at the left-hand side of equation 2 is AC squared. That is AB squared plus length AC squared equal to the right side of equation 1, AB squared plus BD squared. That's what I have over here. Plus the right side of equation 2, AB squared plus BC squared. Then that is therefore AB squared plus AC squared is equal to AD plus AD, adding the like terms, that will be 2AD squared plus BD plus, don't forget that BC is equal to BD. So BD plus BD is equal to 2BD squared. So here is 2AD squared plus, now don't forget that we have equation 3 as BD. Equation 3 is BD equals half BC squared. So I substituted BD for half BC squared. Substituting into this, so that the squared with BD initially, the square is going to affect the new substitute. That's R is equal to, that's 2AD squared plus, opening the bracket, the power here will be distributed over the 10, the numbers in the bracket. So 1 over 2 squared is something as 1 over 4. And I still have my BC squared. 2 can factor out 4 remaining in 2 times. So this is AD, therefore AB squared plus AC squared equals 2AD squared plus half BD squared. And that is the proof. That is the proof. That is the end of the proof. And very interesting proof and clear and very easy to do. So I encourage you to look for more questions of this nature. Prove it. It's going to help you boost your logical reasoning. Right. So next, we shall look at another set of exercises 6 and 7. Exercises 6 and 7. So these ones, you also solve all of these and submit. I'm going to give you more time to do that. I will extend the time. Even if you are not able to finish solving before the end of the lesson, you can go ahead and solve, but I will extend the time and you will see it indicated when you indicated in the post I'm going to create. All right, so the next thing we shall be looking at is angles of 30 degrees, 45 degrees, and 60 degrees. These are the angles that we refer to as special angles. So look at, I have 2 right angle triangles on my screen, one at the right, left, and one at the right. So the left right angle triangle is an isosceles right angle triangle. Length AB is equal to length BC is equal to, they are equal to 1 unit each. While length AC by Pythagoras Theorem is equal to root 2. And of course, isosceles triangle has equal bases or angles, or the base angles are equal. Therefore, you see this is 45 degrees and here it's also 45 degrees. So considering these 3 trigonometric ratios, sine, cosine, and tan, say 45, 45, 45, that is the middle column of my table. Sine 45 is the angles are equal. I can take any of the angles to be my reference angle. So taking the one at C to be the reference angle, recall that sine is opposite over hypotenuse. Opposite 1, hypotenuse root 2. So that sine 45 is 1 over root 2 in fraction. Sine 45 is 1 over root 2 in fraction. Cos 45, we're still looking at this 45 degrees as our reference angle. So this one over here is adjacent, while the 2 remains the hypotenuse. So cos 45 degrees is adjacent over hypotenuse. That is also 1 over 2. 1 over 2. So you observe that sin 45 is equal to cos 45. Finally, for 45 degrees tan 45, we are still taking this as the reference angle, opposite over adjacent. That is 1 over 1, which is 1. So tan 45 is 1. Sin 45 is 1 over root 2, cos 45 is 1 over root 2, and tan 45 is 1. Next, let's look at the triangle by the my right side of the screen. So here I have an isosceles triangle that is divided into 2 right angle triangles, 2 congruent right angle triangles. Now looking at the right angle triangles formed at the left of the isosceles triangle, we have each equilateral triangle, or not isosceles space, equilateral triangle. Each side of the equilateral triangle is 2 units each. So introducing the altitude of the triangle, we discover that it has divided, that bisects the base BC into 2 equal parts, 1 and 1. So from here, you agree with me that in an equilateral triangle, each of its angles is 60 degrees. So this guy is 60. Therefore, this will be 30. Why? Because this line is the bisector. So that divided is the angle at the apex of the triangle into 2 equal parts. So And applying Pythagoras theorem, we saw for the length A, the length of the altitude of the triangle, which is 3. So now we have a complete triangle with all lengths given and all interior angles given. So let's consider the given angle as 30 degrees, the interior angle as 30 degrees. We want to get the trigonometric ratios of sine 30, cos 30, and tan 30. So if the angle is sine 30 degrees, if the angle is 30, looking at sine 30 degrees, sine, don't forget, is opposite over hypotenuse to sine. 30 is 1 over 2, fraction. Sine 30 is 1 over 2, opposite over hypotenuse, because this is the line, the side facing the given angle. Cos 30, this is still the opposite. That means this side here is the altitude of the triangle is the adjacent in this case. So taking 30 as the reference angle, this side is the opposite, therefore here is the adjacent. So adjacent over hypotenuse, that is 3 over 2, because 30 is 3 over 2. Then finally for angle 30 degrees, tan 30 is, excuse me, tan 30 is opposite over adjacent, 1 over 3. Tan 30 opposite over adjacent, 1 over 3. And the last but not the least, looking at the angle 60 degrees. If this angle is the reference angle, therefore the opposite will now become the altitude of the triangle, while the adjacent becomes this half of the base. All right. So let's start with sine 60 degrees. Opposite root 3 over adjacent 2. Sine 60 degrees is 3 over 2. Okay, now cos 60 degrees adjacent over hypotenuse. Cos 60 degrees is 1 over 2. And finally, tan 60 degrees is opposite over adjacent. That is 3 over 1, which is root 3. So you are encouraged to memorize all these values, but better still, if you can remember the triangles, you don't need to cram anything. Remember the triangles, you can always derive these values in fraction. And I will encourage you to memorize, not memorize, understand it, and remember the triangle, because you may get yourself confused. Most students, it happened to me while I was still learning, still in secondary school. It also happened to me. At too many points, I could not figure out sine 30 easily. I know it's either 1 over 2 or 3 over 2. I'm not sure of it. So please, but with the help of the triangles, I was able to solve that particular problem. All right. So here's example 9 and example 10. Okay. Let's look at the solutions to examples 9, 10, and 11. Because before we end this lesson, solutions to examples 9, 10, and 11. All right. Okay. So example 9. It says in the diagram below, if length DC is 4 centimeters, find length AD. In triangle ABC, tan 60 degrees is equal to AC over 4. Of course, don't forget tan theta is opposite over adjacent. So since this is the reference angle given, this is the opposite, and here is the adjacent. So which implies that size AC is equal to 4 tan 60 degrees. And The length of AC is equal to 4 root 3. Why? Because tan 60 degrees is root 3. In triangle ACD, since 45, okay, sorry, sine 45 degrees is equal to opposite length AC over hypotenuse length AD. Okay, so making AD the subject of the formula by cross multiplying, we have AC over sine 45 degrees, which implies that AD is equal to 4 root 3 divided by 1 over 2, because 45 degrees is 1 over 2. So this let AC over this sign over has been converted into division. So of course it means division divided by the fraction 1 over 2. So when you change this division sign to multiplication, of course you know this fraction at the right side will be inverted. That is 4 root 3 times root 2 over 1. Therefore, the magnitude of length AD is equal to 4 root 6 centimeters. Very simple and direct. Example 10. If sine theta is 3 over 5, find the value of 1 plus tan theta over 1 minus tan theta. Solution. So to solve this problem, it's advisable to sketch your right angle triangle and indicate where 3 and 5 should be. Don't forget sine is opposite over hypotenuse. So if this is the given angle or the reference angle theta, it means the opposite will be 3 and hypotenuse is 5. Now by the use of or with the help of Pythagoras Theorem, you can solve for the adjacent, which should give 4. So therefore, tan theta, which is opposite over adjacent, is 3 over 4. Now, we now go into solving the problem. We have 1 plus tan theta, which is 1 plus 3 over 4 over 1 minus 3 over 4. Adding the fraction at the numerator, that will give 7 over 4 divided by subtracting 1 from 3 over 4 give 1 over 4. So this is equal to 7 over 4 times 4 over 1. And that is equal to 7. Very simple and interesting, I believe. Finally, example 7 says town A is 61 kilometers north and 23 kilometers east of D. Calculate the bearing of A from B to the nearest 0.1 degrees. So here is town B. A is 61 kilometers north and 23 kilometers east. So this is where point A is located. The bearing of A from B is the line joining the north pole of B to the line from the north pole of B to the line joining A. Okay, this particular angle is the bearing of A from B. So, and when you check this out, you see that the two given length of the right angle triangle form is the opposite and the adjacent. And of course, tan theta is the trigonometrical ratio that is suitable for this problem. To have tan theta equals opposite 23 over adjacent 61. Tan theta equals 0.3770. Therefore, theta equals tan inverse of 0.3770, which is equal to 20.65. Therefore, the bearing of A from B is equal to 20.7 degrees to the nearest 0.1 degrees. And this this will bring us to the end of this lesson. I hope the lesson was interesting and was clear enough. So I would like you to attempt these questions from your textbook as assignments. We have a lot of exercises and assignments to do before the next class. That is next week. New General Mathematics for SS1, page 146, exercise 11D, numbers 2, 12, 27, and 28. This set of exercises will be due on Tuesday. On or before Tuesday, you are expected to submit these exercises, while others Other ones you've seen earlier at the beginning of the video. You submit those ones today before the end of the day. Maybe before the end of the class, but before the end of the day. So I wish you guys best of luck. Keep learning, and in case you have any question, don't hesitate to ask the question in the platform. Thank you very much. God bless you all. And also remember to subscribe to my YouTube channel and like this video so that you'll be able to see notifications as I add other videos to the channel. I hope you enjoyed this one. Okay, remember to keep staying safe and keep studying. I wish you all the very best, and God bless you all.